Hello, everybody. Welcome back. Today we're going to be looking at Unit 3.5, which is on the kinetic molecular theory of gases. So let's get started. So the kinetic molecular theory gives some characteristics to what makes an ideal, what makes a gas ideal. And it also just kind of talks about some characteristics of gases. So let's look at it. So the first thing says volume of individual particles is close to zero. Okay, now of course we know that, atoms of a gas, they do have volume. However, they are so small, it's basically considered negligible, and any difference in volume between two different gases is also considered to be essentially negligible. We've already talked about the concept of pressure, okay? So this is just a little bit of review, that gases have these completely random motions. They are traveling at high speeds, and when they strike the side of the container, they will exert a force over that area, and that causes pressure. However, one of the characteristics of an ideal gas is that the particles don't exert any forces on each other. If we were in a physics class, a way to say that is that all gaseous particles go through perfectly elastic collisions, okay? And while that might not be quite correct, it's a pretty good assumption when you're looking at a gas. This last piece is almost more of a definition. When we talk about the temperature of anything, it doesn't have to be just a gas, okay? Temperature is directly proportional. That's what that little symbol means that looks sort of like a little crab claw. Directly proportional to the average kinetic energy of that sample. Okay, now let's review that term. You may have heard that term before. If you've taken physics, kinetic energy is the energy of motion. So if temperature is proportional to the average kinetic energy, if you think about it, when you raise the temperature of anything, all you are really doing is causing the particles to move faster and faster and faster, okay? So that's an important concept to understand there, okay? And you'll have a lot of AP questions in both multiple choice and free response that will try and trick you, and they'll give you all this information, two different situations, but if you'll notice, the temperature stays constant between the two situations, and they'll say something about the average kinetic energy is different, and no, it isn't. As long as temperature is constant, so is the average kinetic energy. Okay, for those of you that take physics, you may be familiar with this equation, okay? This one is actually on our equation sheet. It's an equation that relates, so kinetic energy is equal to 1/2 times mass times velocity squared. Okay, so this equation relates kinetic energy to the speed of particles, okay? And if the kinetic energy is going up, excuse me, then the temperature must be going up. We're going to see gaseous particles moving at faster speeds. And there is something called a Maxwell-Boltzmann distribution curve, which you'll see frequently on the AP exam. And what we've got here, okay, is, let me take that down for a second. You have particle speed on the x-axis and number of particles on the y-axis. Sometimes you'll see the y-axis labeled with something like frequency factor, or percentage. It just essentially means how many particles have that speed, okay, within a sample. And if you look at the blue curve, okay, where the temperature is low. So this would be a sample of a cold gas. All right, we see this, it's not quite a bell curve, it's a little bit different shape than a bell curve. All right, but we see that the greatest amount of particles in that cold gas have whatever, that's not a very straight line, sorry, whatever that particular speed is. But in any sample of gas, guys, you're going to have a distribution. You're going to have some gases that are moving more slowly. You're going to have some gases that are moving at high speeds, okay? There's a variety, okay, of speeds within any sample of gas, all right? Now, when we raise the temperature of that gas, okay, the curve flattens out a little bit, and that confuses students sometimes. You might think, well, you know, shouldn't the curve be higher? But look at where the greatest percentage of gases are now falling. They're now falling at a higher speed, and that should make sense to you. If you raise the temperature of a gas, the speed of the particles is going to increase, okay? It's still a distribution. We're still going to have some gases, you know, in this area that are moving more slowly. We're still going to have gases that are moving more quickly, but where the greatest percentage of gases is falling, if here's where the cold falls, and here's the greatest percentage where the hot gas falls, it's at a higher speed, okay? One thing to also note, and this is, I'm not teaching calculus in this class, I assure you, but the area under those curves is equal, okay? The area under each curve is representing all total gas particles. And so the curve flattens out a little bit because the area under the curve is going to remain the same. So I want us to look at a practice problem here, and I know it's a little bit hard to see, and I apologize for that, but let's talk through this question. Okay, it says the graph above, meaning this one, represents particle speed distribution for a gas at a certain temperature. Which of the following graphs represent the speed distribution of a heavier gas but at the same temperature? And we're going to indicate the new graph with the red arrow. Okay, so we've talked about a Maxwell-Boltzmann distribution curve at two different temperatures, but what about if we're comparing two different gases? Okay, well, heavier gases, okay, I'm looking at my noble gases and I'm looking at some of the big boys like radon, okay? Radon atoms are big boys, okay? Heavier gases move on average at a slower speed. Smaller gases, again, I'm looking at my noble gases like helium, on average, move much, much faster, much higher speeds. Okay, so molar mass has an effect here. A heavier gas like radon is on average going to move at a slower speed. So I want you to look at these answer choices and see which curve do you think makes sense. So you can pause the video here if you want and think about it. All right, hopefully you selected that as letter B as your answer, okay? Because it's a heavier gas, it's going to, on average, be moving at a slower speed, so the peak needs to be more to the left, and it's going to be a higher peak, okay? It's going to be thinned out a little bit. Remember, the area under the curve needs to be equal in both situations. So that's it for kinetic molecular theory. I hope you've learned a little something today, and I look forward to seeing you next time.